So let's see. Form of the information determines the type comments. Type comments determine the template. Template determines the form of the functions. Then when we have repetitive functions, we can abstract them into an abstract function. Could there be a way to shorten that route? In fact, there is. In fact, there's a way to go from type comments directly to abstract functions. And then lots of the functions we write just become very short. We're not going to take quite that shortcut in this video. What we're going to do in this video is go directly from templates to abstract functions. And that will take us all the way back to something we saw when we first looked at list functions. Remember the table of list functions, and we just looked at what to fill into each position in the template? Now what's going to happen is lots of our functions on lists and arbitrary arity trees or any other kind of recursive structure are going to get real short, and generating the abstract function is going to get real automatic. I'm in fold function starter.racket, and at this point in the course, the type list of x means list of x is one of empty or cons x list of x. And we interpret that, what is there to interpret it as? A list of x. And the template for list of x is the ordinary list template. Two cases con, if it's empty something, otherwise the first of locks, fun for locks, rest of locks. And I've renamed the parameter to locks because it's a list of x. And now here's a problem. And the problem is to design an abstract fold function for list of x. So you might ask, what the heck's a fold function? Well, let me show you. Here's the idea. The idea is to design an abstract function based directly off the template. So again, I'm going to work backwards through the steps of HTDF. I'm going to copy the template, and I'm going to call the function fold. It's actually going to be the foldr function, but I'll just call it fold. Then I'm going to say, gee, there's two sets of dots. I'm going to introduce one parameter for each set of dots. And I should give them some good names. Now, this one is the base case result. So I'll introduce a parameter called b, and I'll use it in this position. Notice I'm also getting rid of the parens, because b is the final result. It's not a function of no arguments. So there, b is now standing for the first set of dots. And this one is a function that's called to take the first of the list and combine it with the result of the natural recursion. So I'll call that fun. And just by convention, we put the function arguments early in abstract functions. So I ordered the arguments that way. You could have ordered them the other way. I just want this to end up being exactly like foldr. So now I've got the function. Now I've got the function. Now let's do some tests for it, some check expecs. Well, it's the abstract function for the list template. So I know some of the things that it can do. If I say fold with plus and 0 and list 1, 2, 3, I get the sum of that list, which is 6. If I say fold with times 1 and the list 1, 2, 3, I get the product of that list, which is also 6. And I could try those to make sure I understand this function properly. Oh, what happened here is I forgot to rename the recursion, and I forgot to add the parameters to the recursion. You're always making mistakes in this business. Now I've renamed the natural recursion, and I added the parameters in the natural recursion. Now these tests are tests from later in the file, so we're not going to worry about them. These failing tests are from later in the file. Let me comment that out so we won't see that ugly highlighting. My tests for fold are working. So now what's the purpose? Well, if you didn't have a more abstract way of writing the purpose, if you didn't know that this was fold_r, it would be enough to say the abstract fold function for list of x. Because that's what a fold function is. You take the template, you define a function based on the template with an additional parameter for each set of dots. And that's what a fold function is. Now let's think about the signature. Well, you know that this isn't, even though both of these examples are list of number, it started with the list of x template. So you know that this third parameter is really list of x. Now, this makes it quite clear that the result isn't list of x. It isn't even a list at all. It's something else. Now, it happens to be number in both of these cases, so you might want to just put number there. But what you should do instead is think, can I make it do something else? Can I make it, for example, quote, add up some strings? For example, can I do fold string append with the empty string as the empty sum, and list A, B, C, D, E, F. Let's see, adding or appending all those strings together should produce A, B, C, D, E, F. And that test is working. The test that's failing is later in the file. So that test is working. So that tells me that the result isn't always a number. It can be something else. Now, in both of these cases, it's list of string to string. So that might make me write x there. Now I got to try to make it do something else. I got to see, can I construct an example where the final result isn't the same as the type of the elements of the consumed list? So you could try to construct that example, or you could look at the code and say to yourself, well, each of these has to be an x. Those are always the type of the first argument to the function. So let me back up here and say the first argument to the function has to be an x. The second argument to the function is the result of the recursion, which of course is the type of the base and always the result of the function. There's nothing here that says that this type and this type really have to be the same. So this could actually be y. And then if this whole thing is going to produce a y, then that means that the type of the second argument to the function is a y, and the function has to produce a y, and also the type of b has to be y. So what that says is, give fold a value of type y, the base case value of type y, and a list of x, and a function that consumes an x, a y, and produces a y, and it will go through the entire list producing the final y. And that's in fact the signature for folder. Now that you have fold, if you didn't have it already, but now that you have it, you can of course use it in lots of ways. You've already done some in an earlier video, so I'll just pause here and ask you to do it again if you're a little unsure about how fold is working, just to improve your confidence that you understand what fold does. So here's kind of an optional in-video quiz question for you. And here's the result I ended up with. It, of course, is exactly equivalent to this first check expect, or it's essentially equivalent to this first check expect. The function argument to fold is plus, the base case value is 0, and the list argument is the list. Here's a similar one for adding together a list of images. Do this exercise now. And here's the definition I ended up with. I call fold with beside as the composition, with a white square as the base, and with the list of images. If you remember all the way back to that table that I showed you in the first week on list functions, and I showed you the different ways you could fill in that table, you can now see the different ways that you can fill in fold. Plus and 0 gives you sum, times and 1 gives you product, beside and a blank square gives you juxtapose. You can do all sorts of things with fold, because fold really is the abstract function for the list of X type. It's the abstract function for the list of X type. You take the template, you add one parameter for each ... in the template. There's a funny thing you can do, which is to give fold parameters that will just produce the same result that comes in. So if I just say copy list of locks, and I call fold, and in the composition position I put cons, and in the base result position I put empty, then this function copy list just produces whatever result it's given. Copy list of empty produces empty, copy list of list 1, 2, 3 produces list 1, 2, 3. Because we're filling cons into this combination position and empty into the base position. And again, going back to that table, the line for copy list is cons and empty, and that just produces a copy of the list. So that's kind of neat. That's fold for a list. Now watch this. Design an abstract fold function for element. Remember, element was the arbitrary arity tree that we looked at last week. Well, there's the template for element, in which I've already grouped it with local into an outer function and the two inner functions. So if I start with that, and now I'm going to design this abstract fold function. Let's see, I'll put the design down here. It's going to be called fold element. I can't call it fold again because I already used that name. Fold element, and now let's see. There's two function positions. There's combine 1, which will be here, and combine 2, which will be here. And there's one base, which will be here. And there it is. I've got the fold function. Well, let's see. What's a check expect for what it can do? Well, this is going to be a little bit more complicated because C1 and C2 are more interesting functions. But let's try to do a check expect for the case where we build a list of all the names in the tree. We're going to need a helper function for that. So I'm going to start with a local. And we're going to say fold element. And the argument, let's say the argument is going to be D6. That'll be the actual tree. So now we need two combination functions. Let's see, C1 goes right here. And I'm just going to define it here with that name. Define C1, and it consumes three arguments. It consumes a name, a data, and the result of the natural recursion, which in this case, of course, is going to be a list of names. And what does this thing have to do? Well, it's going to ignore the data and cons the name onto LOS. And now let's see, what does C2 have to do? The reason I'm defining C1 and C2 using a local is they're a little bit more complicated, or perhaps they're more complicated anyways. What C2 has to do is, let's see, both of these natural recursions are going to produce a list of names or a list of strings, and I just have to combine them together. Oh, well, if I've got two lists of strings and I want a single list of strings, that's just append. C2 isn't really that complicated. So let's see, it's fold element, C1, append, and empty is the base. And does that produce, what's the result we're after here? Remember what the tree looks like. It's D6 comes first, and then D4, and then F1, and F2, and then D5, and then F3. F3. That would be the result. Let's see if that works. Whoops, what did I do wrong here? Cons expects 2 arguments, but found only 1. Oh yeah, that's not right. I need to cons and onto LOS. And this test is failing. It means that this test is succeeding. So pretty cool here. I managed to make a list of all the names in the tree using the abstract function fold element. So the purpose is the abstract fold function for element. And of course that means it's also for list of element, because that is involved in element. Probably just leave that out because it originally consumes element. Now we got to get the signature. Let's see. In this template, I've already got the type produced by these 2 selectors annotated here. And I'm going to start by adding 2 more annotations. There are these 2 mutually recursive functions, and I don't know what types they produce. I don't know what types they produce yet in the abstract function, because they might produce different things depending on C1 and C2. I'm going to start by saying fun for element in general produces X, and fun for LOE in general produces Y. I've just introduced 2 type parameters to let me talk about what fun for element produces and fun for LOE produces. Why was that a good idea? Well, watch. Now let's look at the signature of fold element. Well, let's see. The first argument to fold element is C1, and C1's a function. So I'll just start by saying, well, it's a function, so it's going to look like that. Now let's see. It's a function of 3 arguments. The first one is a string, so I'll say string. The second one is an integer. The third one is the result of fun for LOE. Well, what's the type of the result of fun for LOE? Well, I decided that that was going to be a Y. So I'll just put Y there. So let's see, C1 consumes a string, an integer, and a Y, because it's the fun for LOE. And what does it produce? Well, I decided it was going to produce X, so I'll just put X there. Now I'm working on the second argument to fold element, in other words, C2. C2 is a function. It gets used right there as a function, so I'll just start by putting that. Now I'll fill that in. It's a function of 2 arguments. The first is a result of fun for element. And fun for element produces X, so that means the type of the first is X. The second argument to C2 is a result of fun for LOE. So that means its type is Y. And C2 has to be willing to produce whatever fun for LOE is supposed to produce, because C2 is called in a result position for fun for LOE. So that means C2 has to produce a Y. All right, that's the C2 argument to fold element. Let's look at B. What is B? Well, B is the base case result of fun for LOE. That means B has to have the same type as fun for LOE produces. So that's got to be a Y. B has to be of type Y. And now we're looking at E. Well, E, of course, is an element. And finally, we need the result type of the entire fold element. Let's see, fold element produces whatever fun for element produces. And fun for element we decided produced x. So this whole thing is going to produce x. So there you go. There's the signature for a mutually recursive abstract function, an abstract function operating on an arbitrary arity tree. And I did it basically the same way that I've been doing the signatures for abstract functions from the beginning, with the one addition that in this case, because there's these two inner functions, I went ahead fairly early on and gave type parameters for each of their results. So I said fun for element produces x and fun for LOE produces y. And then I just used the type inference, reading the types off and building up what I could tell about the types to get to this signature. Abstract fold functions on more complex data, on types with mutual reference, are pretty cool. They let you write some very interesting functions very compactly. Why don't you play around with them in the exercises coming up?